Our next presenter is Professor Ravindra Gaitu. Dr. Gaitu is currently the Dean for Industrial Consultancy and Sponsored Research and V.S. Raju Chair Professor at the Department of Civil Engineering at the Indian Institute of Technology, Madras, Chennai. He obtained his PhD degree in structural engineering from Northwestern University. He has co-authored more than 500 publications, of which more than 100 are peer-reviewed journal papers. A fellow of the Indian National Academy of Engineering, which is in fact the highest honor in India. Ravindra is the immediate past president and a fellow of RILEM and a foreign member of the Russian Academy of Engineering. Please help me welcome Professor Ravindra Gaitu. Ravindra.
Thank you very much, Nemi. So thank you for having me here. It's certainly a pleasure to join several of my friends on this in this session. So I'm going to introduce a new initiative that we've started, emphasizing technologies for low carbon and lean construction. This is headed by my colleague Manu Santanam. And we are a group of about 20 faculty members. We have about 30 research scholars, several collaborations around the world, and certainly with RILEM and ACI, we're looking forward to more collaboration. The research team has expertise in construction materials, construction management, and building science and automation. So our emphasis, or the questions that we want to address, is how can we reduce the material wastage? Can we use waste from other industries other than construction in sustainable construction? And along with that, we also want to look at process waste. And there comes in the lean construction. We want to decrease defects, decrease waiting time, decrease the transportation time and cost, and so on, and lead more towards sustainable construction. So we employ a systems thinking approach where we know the problem. We know that there is a lot of wastage. There is construction process waste. There is deterioration, lack of durability in structures, and we want to reduce the carbon footprint. Therefore, we go to basic scientific research. Beyond just the physics and chemistry, we also want to use computing power. We want to use sensors to understand better the linkages between the material and the structure and its performance. For this, we want to develop a test bed, a technology test bed where we think that we can take materials, new waste or more emerging waste, and see how they can fit in back into the construction process. So these could be waste that are coming from the construction industry or from other industries. We take this experience to management. We look at organization and try to formulate policy, which we think is very important, not stopping at what we can do in the lab, but influence policy so that construction really changes. So our approach is based on the life cycle of the element, life cycle of the structure, life cycle of the material, starting off with reducing waste as the raw material, use more of waste and have less wastage of material. We would like to map waste materials that could be available for economic, socio-economic construction. We look at techniques such as BIM for design and new technologies such as prefabrication and 3D printing in construction. All this we want to make as durable as possible so that there is no repetition, there is no repair, and there is reduction of the raw material used. Eventually, when we want to demolish, we want to see how much of this material can come back to the structure. So there is a lot of emphasis on the logistics, on the supply chain of the construction demolition waste and make it come back to concrete. Finally, we would recycle this so that we consider the circular economy for construction. For this, we are looking at 4 elements or 4 tracks. The first, as I mentioned, is basic scientific research, where we are looking at physicochemical processing of the waste so that we can go for high volume usage in construction, use this waste in new technologies such as 3D printing, more of prefabrication, pavements, and so on. Correlate the material characteristics to the final properties, the performance that we require in concrete. Emphasis is always on durability and service life. We want durable construction at low carbon footprint. And for this, we are looking at sustainability indicators and life cycle assessment. Some examples of each of these tracks. As I said, we are looking at concrete performance to relate the characteristics of the waste to concrete performance when we use these as supplementary cementitious materials. So we are looking at the pore structure, its evolution, connectivity, linking it to chloride diffusion, carbonation, and so on. We are also looking at sustainability indicators based on life cycle assessment. One example of what we've been able to do to connect the microstructure to macro performance is this image that shows us the relation between diffusion, represented here as the migration coefficient, and the tortuosity based on electrical conductivity. And we see here this very nice trend. And at the lower end, higher tortuosity is given by materials which have low clinker, like limestone, calcine, clay cement, fly ash. And at the upper end, with lower tortuosity and higher diffusion, we find the ordinary Portland cement systems, clearly indicating the reason why we get better durability performance under chloride attack when we have lower clinker and more of supplementary cementitious materials. We are also looking at life cycle assessment. So in this graph here, we see the CO2 emissions, how we have quantified them coming down from ordinary Portland cement to Portland fly ash cement, slag cement, and so on. And this is because of the reduction in clinker. So these data we've had to collect directly from the plants because we don't have databases, we don't have catalogs in India. The other area that we're looking at more is biomass ash. A lot of biomass is used in India for generating electricity, and this will continue to do so. So we would like to establish a relation between the composition and the reactivity, have a framework which emphasizes high volume utilization, map the agro waste. India has an extensive agriculture sector. So we want to see where the agro wastes are available so that we can use this fruitfully. We have some example of biomass ash bricks. So here we see a prototype that has come about by combining the ash with other binders, checking the strength and other properties before we go on to a prototype. The next track beyond the basic research is applied research leading to technology development. So here we are looking at know-how development, patents, and so on, where we are going from the lab to the field. 3D printing is certainly having a lot of emphasis, and we are looking at software and tools, light tools, easy to use software systems that can help minimize waste so that it's not tedious to have the computation and so on. We have to develop sustainability indices that help the user, the contractor, someone who is at the site to compare different materials and choose what is more sustainable and having lower carbon footprint. So again, some examples. We are looking at durability as a way of achieving sustainability. So sustainability through durability is a very strong emphasizing factor. So we are looking at the corrosion threshold of coated, uncoated steel reinforcement in different concretes, different binder systems. We're looking at carbonation. Not much data is there in temperate and tropical climates. So we're looking at carbonation, service life modeling. Life is very important. We want to have simple models, maybe nomograms, which will help us choose the materials that will give us more sustainable structures. This is an example of long-term studies. This has gone for about 9 years, 8+ years, where we are looking at carbonation in the natural environment. and we are trying out different concretes. We have the ordinary Portland cement system with slag, with fly ash, and the limestone calcine clay system. We are looking at an easy to use sustainability framework. So here we see a framework based on energy on the x-axis, energy and strength coming in the x-axis. In the y-axis, we have defined something called the apathy index, which looks at the carbon emissions, the carbon footprint, and the durability. And based on this, of all the different choices that a contractor could have at the site, they can choose the concrete that is more sustainable. On the other hand, we are looking at construction automation. As was already mentioned on this session, labor is becoming difficult to get at the construction site, and we want to take advantage of this situation, bring in more automation, decrease defects, and increase quality. So construction automation is also an emphasis, along with 3D printing with the software, materials, and systems. In 3D printing, we are mentoring a startup of young former students of IIT Madras, and this is one of the houses that they have built. We are also looking at integrating 3D printing with robotics for placing reinforcement, for placing the service lines, the ducting within a 3D printed structure. So that is track 2. Now, track 3 would be larger scale, something like a test bed. So we are putting in visualization, we are putting in artificial intelligence, so that if someone brings up a waste, we encounter a waste, can we have a quick way of testing it out, running through the different processes involved in towards final usage of the material in construction, optimizing it. And then we also want to have some sort of an adoption strategy that will come out of simulation and game-based learning. So this would be sort of the diagram sketch of the testbed, where we have a waste source. It comes in, we can process it, we can try it out, we can sort and check it with concrete or other construction material, and then we eventually turn out a high quality concrete. Some wastes that are being studied right now are pond and bottom ash from power plants, urban demolition waste, bio-mined plastic waste that is there in the landfill. Coconut coir, we have a lot of coconut plantations, and finally gray water. India is a thirsty country for water like many other parts of the world, and we feel that we have to use water that is coming from sewage lines, which is usually just let off. If we can put it back into construction, that would be a great idea. So we have some experience already. This is an experience about recycled asphalt pavements used as concrete aggregates, where we take the distressed flexible pavement and go all the way through until it becomes a concrete pavement. The final track is the policy and change in the organization. We strongly believe that just developing a material, developing a structural design doesn't really end up with people using it. So we want national maps showing the availability of waste materials based on socio-economic environmental aspects. We need strategies to modify, to adapt, to adopt these lean construction practices, new technologies, and we need a framework that will include the supply chain and the life cycle, and finally policy. So again, we have experience, there is motivation for doing this. We need to make significant changes in the project delivery approaches, policies, so that construction industry adopts innovation, quality, and user satisfaction. We want to emphasize the possibility of innovative construction materials, digitalization, automation, change project governance. Contracts, for example, we want to have model contracts, because often we find that when a new material system is introduced, people don't know how to include it in the specifications. Then the infrastructure planning and urban development will start. Again, we have experience. We have participated in national level committees on public-private partnerships, housing and infrastructure reports, at the state level and at the national level in terms of housing, ports, public-private partnerships, for example, in tollways, and so on. Finally, within this track 4, we want to improve safety. Safety is a major constraint, important aspect in construction projects. Lot of concern. So we want to go to the next level of safety, safety 2, where we want to look at the overall safety, not just the outliers. So there we need system thinking, resilience, and the goal would be a system dynamics-based simulation game so that we can simulate what happens when we change things. If you introduce something where we have training, we have other norms in place, how does the safety change? The impact could be capacity building, management training for industry stakeholders. Again, an example, we've used system dynamics to simulate what would happen in terms of accidents. So this is a curve showing how accidents start decreasing when there is a systems change made, training made, or other aspects that are changed in the way that construction is done. So these are the different tracks. This is our goal. So I would stop there. Thank you for the attention. Please visit us at this website for more information. Thank you.